In Chapter 6 last semester, we talked about how to calculate the delta H of a chemical reaction. Right? We mentioned that enthalpy is a state function, so we can use the total enthalpy of your products and minus the total enthalpy of the reactants to calculate the delta H of a chemical reaction. Right? Similarly, we can do the same or using the same approach when we want to calculate the change of enthalpy for a chemical reaction, the delta S, right? So because delta S is also a state function, right? So here in this slide, we introduce this term called the standard entropy of a reaction, right? So had this symbol of delta S not reaction, right? So delta S, the change of entropy, does not indicate is the standard state, and the Rxn represents for a reaction, right? So the Rxn is written at the subscript position. So the definition for this term is the entropy change that occurs when all reactants and products are in their standard states. So when we look at this chemical reaction and try to predict the sign or try to predict the sign of this delta H, so one way to do so is looking at the coefficient of the gas, right? Because the gas has a much greater freedom and motion than the solids and the liquids, right? So if we can calculate the total number of coefficient for gas molecules on the reactant side and the product side and compare them, we can basically predict the sign of this delta S, right? For example, in this first reaction, right? So for this first reaction, on the side of the reactants, we only have 1 mole of gas, right? The other reactant is a solid. But for the products, we have 2 moles of these products, right? So for the products, we have more gas molecules, so more freedom or higher entropy. So because delta S is the entropy of the products minus the reactant, so in this case, it's greater than 0. Right, for the second reaction, right, we have 1 plus 3, a total of 4 moles of gas, but only ended up with 2. Right? So in this case, 2 minus 4 is less than 0. So the delta S is less than 0. Right? So the first two cases, right, we have different number of moles of gas molecules. Right? So we can, based on the total of the coefficients for the gas, right, in the reaction, to determine the sign of the delta S. Right, so when we have similar total number of gas molecules on both sides, right? So in this case, we have one here and another one here, right? So some structural information can also help us determine which side has a higher entropy, right? For example, in this case, right, we have this ring structure, right? So after reaction, after we heat it, it opened up, right? So compared to this ring structure with this chain structure, right? So this one will have more freedom, right? So because the ring structure, it is confined, right? So it limits the movement of these carbons. But once it becomes a chain, right? So this carbon have more freedom. So the product has a higher entropy than the reactant, so it's still greater than 0. But most of the time, right? So even we have a reaction without a significant change of volume and not too much information from the structure side, it's hard to predict the delta S, right? By just looking at this the equation, right? So in terms of calculating the delta S of a reaction, we can use the appendix B, right, that we introduced in the previous video, right? So that table, it has all the standard molar entropy for all the common substance and the molecules, right? So all the items, right? So if you have a chemical reaction, right, so you can look at the identity of each substance and using that table to find their S naught right? So in this example, right, so we want to calculate the delta S of the reaction, right? So we want to calculate the delta S of the reaction. Right, so the general equation is that we want to know the sum of the delta S for all your products minus the sum of the delta of the S of all your reactants. Right, so here we have again 1 plus 3, a total 4 moles of gas. Right? On this side we have 2. So before we calculate, we know our answer is going to be less than 0. Right? So that's the first thing that you're pretty sure with. And then we're gonna look at this appendix B. Right? So this appendix B looking for nitrogen gas, or pay attention to the physical states. Right? So different, same compound or same molecule, different physical state give you different delta S naught values, right? So we were looking for gas phase nitrogen, gas phase hydrogen, and the gas phase ammonia. Right? So using that table, we find out that for nitrogen in gas phase, right, this is the S naught, this is the S naught for the hydrogen, I mean the nitrogen, and this is for the hydrogen, right? This is for ammonia. So this is for ammonia, right? So we have products minus reactants, right? So here is the total S naught of your products, right? You have 2 mole of those, right? So you multiply the S naught of ammonia by 2, right? So this is in the bracket is the sum of S naught for your reactants, right? So you have 1 mole of nitrogen here, and the 3 mole of hydrogen here. Right, so it's exactly the same approach for calculating the delta H. So at the end you get negative 197. Right, so as we predicted, it is less than 0. So let's look at another example problem. Right, so we have this chemical reaction. Right, so we want to know the delta S, right, of the reaction at the standard state. Right, so the question says calculate this value for the combustion of 1 mole of propane, right? So this is propane, and it has a coefficient of 1. And so then this is room temperature, right, which is 298, right? 298 Kelvin. Right, so again, we can use the table in appendix B, right? Looking for the S naught value, or standard entropy value for all of these compounds in the reaction. Right, so for your products, you have 3 mole of carbon dioxide, 4 mole of water, right, in the liquid phase, right? Pay attention, this is a liquid, right? So here, so inside this first bracket, you have the sum of the entropy for all your products, right? Then minus, right? So minus the total of your reactants, right? So that is 1 mole of propane and 5 mole of oxygen. So looking for those values in the table and substitute the numbers here in the equation, right? So you're gonna end up with negative 374 joule per Kelvin, and the notice is less than 0, right? So we can also predict that, right? So for the reactants, you have 1 plus 5, which is 6, but for your products, you only have 3, right? Because water is in liquid phase. Right, so that's why the delta S is less than 0. Remember that the second law of thermodynamics indicate that for a reaction or for a process to be spontaneous, right, we must have a positive delta S universe. Right? So delta S universe is the sum of the delta S of the system plus the sum of the delta S of the surrounding. Right, so for this reaction to be spontaneous, this delta S of the universe must be greater than 0, right? Meaning that the sum of the delta S of the system, right, plus the sum of the delta S of the surrounding must be greater than 0. Right, so earlier we've been looking at how to calculate the delta S of the system. right? But again, that doesn't mean the reaction is spontaneous for sure, right? So we must know how to calculate the delta S of the surrounding, then add them up so we can determine whether the reaction is spontaneous or not. Right, so for a say if you have an isothermal reaction, right? So for this system you have a isothermal reaction. Isothermal reaction means that the heat is released, right? So for the heat is released from the system to the surrounding, right? So for the system you're losing heat, so the Q, the sign is less than 0. But for the surrounding, it absorbs heat, so the Q is greater than 0. Right? So when more heat is introduced to this surrounding, right, the higher energy level will introduce more microstates. So you have a higher freedom in the surrounding. So the delta S for your surrounding is greater than 0. Right? That's due to this more energy, or you can think as a higher temperature. Right? So the kinetic energy increases. Right? So, but on the other end, for endothermal reaction, the system requires heat, right? So it absorbs heat from the surrounding. So the system heat is greater than 0. But for the surrounding, because losing heat is less than 0. So it's less energy available for the surrounding molecules. So the delta S for the surrounding is less than 0. Right? So think about the relationship between this heat transfer between the system and the surrounding. Right? So if you have a chemical reaction that you can quantify this change of heat, right, in either direction, that means this number you calculate is equal to the number of to the surrounding, but with the opposite sign. Right? So that means for the delta S of the surrounding, if we know the change of heat for the system and putting a negative sign in front of it, that negative Q system is the Q for the surrounding, and divided by the temperature when this process happens, that will be the delta S of the surrounding. Right? So remember, Q has the unit of J, Joule, and temperature is in Kelvin. Right? So remember this equation. Right? So when you have a process that happens at a constant pressure, right? Remember this heat is equal to Q plus W. W is the work, right? So W is the PV work, right? So the change of volume accompanied by the change of pressure, right? So if this process happens at a constant pressure, meaning that you have no work done, right? So only heat. So that heat is also equal to the energy enthalpy, right? So the enthalpy. So Q will be the enthalpy. So that means for the delta S surrounding is also equal to the negative delta S of the system, right? Which is equal inside the circle, which is equal to the delta H of the surrounding, right? Divided by the temperature. This is the fixed temperature that this process happens, right? So because the temperature is on the denominator, right? So you can imagine that if this reaction happens at a very high temperature, right, the heat released, right, to the from the system to the surrounding, or the heat absorbed, right, from the surrounding to the system, right? So it doesn't, this delta S change will be small, right, when you have a bigger denominator, right? So when this temperature is high. But on the other hand, if this reaction happens at a low temperature, the same amount of change of heat will cause a higher change of a delta S. Right. So a good analogy is that, say, you have some money in the bank account, right? Say you have $1,000, right? So if you deposit another $1,000, so the amount increase is 100%, right? So from 1,000 at the beginning, and then increase 1,000, so it increased by 100%, right? So however, if you're a millionaire, right, you have $1 million in your bank account, and then by depositing the same amount of money, which is $1,000, it only changed by 1%, right? So in that analogy, say if this delta S, right, is the change of the percent, right, the change percentage in your bankroll, right? So it totally depends on the denominator of how much money you have at the beginning, right? So if you have more money, it means you have a higher temperature, right? So the amount of money you added will cover a very small percent, right? But if you have very little money to start with, the money you add will cover a higher percentage. So now let's look at a problem to determine whether the reaction can happen spontaneously or not. Right, so at 298 K, right, we have this reaction again, right, so the formation of ammonia from nitrogen and hydrogen. Right, so it tells us that for the system, right, at this temperature, the delta S is negative 197. Right, remember this number here we calculated based on the S naught of the products, right, minus the S naught total S naught of the reactants. Right, we did that in the previous example. Right, so we know the delta S of the system, but to determine whether this reaction can happen, right, spontaneous or not, we must know the delta S of the surrounding. Right, so we must know the delta S of the surrounding, and then add them up. Right, so we can add these two up, where if it's greater than 0, that means it's spontaneous. Right, so here we want to calculate this. Right, so for this delta S of the surrounding, right, so we must know the delta H of the system, right, divided by the temperature. Temperature is given, right, so it happens at this temperature. So we know the temperature, so we need to know the delta S of the system. Right, so for this delta S of the system, we can use the knowledge we learned in chapter 6. Right, so again using this appendix B. Right, so looking for the heat of formation. Right, so we're looking for heat of formation, this delta H F, right, of each substance in the chemical reaction. Right, so here we have 2 moles of ammonia, right? So that's 2 moles of ammonia times the heat of molar, right? Molar heat of formation for ammonia, right? So in the table we can get this value here, and this is for your products, right? So minus your reactants, right? In this bracket here. So again, these numbers come from the appendix B. And also for elemental substance, you notice, right, they're equal to 0, right? The heat of formation is equal to 0. Right, so for this delta H of the reaction, we got is negative 98.1 kilojoule. Right, so this is for the system, right? This is for the system. Right, so for the surrounding, you need this negative sign here. Right, so the negative delta H of the system is the delta H of the surrounding. Right, so we want to convert this kilojoule into joule, right, because that's the unit for delta S. So after the calculation, we got 308. Right, so now we have a system with a negative 197. Right, but for the surrounding, the delta S is 308. Right, so the overall is 111, which is greater than 0. So this reaction actually happened spontaneously, right? Although for the reaction itself, the delta S is less than 0. Right, so in the textbook, right, so for the surrounding, right, we don't because it could be anything, right? So we don't indicate this standard state, right? So the surrounding could be anything outside your system, right? So we don't write this not here. Right, so this figure here, right, indicate the relative scale of each delta S value. Right, so for the system, you have negative value. Right, so for for this reaction to be spontaneous, right, the surrounding delta S must overweight the negative value of the delta S for your system. Right, so this is a much higher delta S surrounding, right, in terms of the magnitude. So overall, you have a positive delta S. For a process approaching equilibrium, right, when this reaction is at equilibrium state, we can say the delta S of the universe actually equal to 0. Right, so that means the system delta S and the surrounding delta S is the same but with a different sign. Right, so for example, if you look at the water um, evaporates, right? So from liquid to a gas at 373 Kelvin, right? So for this system, we can calculate the delta S, right? So by getting the delta S of the products minus the S of the reactant, right? So we got 109.1 joule per Kelvin, right? For the surrounding, the delta H of this system is equal to equal to this number, right? So by putting a negative sign and then divided by the temperature, we got the delta S for the surrounding. And then notice they're just equal but with a different sign, right? So overall, for the universe, right, the delta S is equal to 0, right? Because at equilibrium is no longer processing, right? So there's no more freedom change. So no matter what is the enthalpy change, right? No matter what the sign of this delta H, a reaction is spontaneous or a reaction occurs because the delta S universe is greater than 0. Right? So there are few scenarios that this delta S universe could be greater than 0, right? Considering the different scenarios for your delta S system and the delta S surrounding, right? So for example, when you have a isothermal reaction, right? So we know for isothermal reaction, right? So for isothermal reaction, because heat is released to the surrounding, right? So we know the delta S of the surrounding must be greater than 0, right? So it's greater than 0. So in these first two A and B, right? In this first two picture, because the system, right, has is isothermic, right? So isothermic means delta H is less than 0, right? So they're both less than 0, right? So meaning that for these two scenarios is isothermic, right? So their delta S surroundings all positive, right? Greater than 0, right? So in this first case, if your system is also has a delta S that's also greater than 0, right? For example, if you have more gas generated, right? So that your overall delta S universe will be also greater than 0, right? So you have two positive number add up together, so it must be positive, right? So in this second case B here, right, say it's still in isothermal reaction, right? So the surrounding delta S is still greater than 0, but for your system, right, the delta S is less than 0, right? So in that case, for this reaction to be spontaneous, right, so the delta S surrounding must overcome the negative delta S of the system. Like the example we looked earlier, right, for the formation of ammonia. Remember that one? For the system, it has a negative delta S right here, but for the surrounding, right, the magnitude is much higher and it is positive. So overall, you still have a delta S, a universe that is greater than 0. Right, so for the third scenario is that you have a endothermic reaction, right? So in this case, delta H is greater than 0, so it's an endothermic reaction. So with the endothermic reaction, the heat is flow into the system, right? So the delta S, right, will be greater than 0, right? Because you have more energy state, you have more microstates, so you have higher freedom for a system, right? Because the heat is flowing into the system. Right, so then we need to look at the magnitude of the delta S for the surrounding, right? Because for the surrounding, you lose heat, right? So the delta S is less than 0. So you have to compare the magnitude of the delta S system and the delta S of the surrounding, right? So if the magnitude of the system for delta S is greater, then overall you still have a delta S universe that's greater than 0, so the reaction is still spontaneous. So overall, right, to conclude, this is what you want, right? So to calculate whether the reaction is spontaneous or not, right? You want this to be 0, and which means that you have to know both the delta S of the system and also the delta S of the surrounding, right? And then you have to you want the sum of these two to be greater than 0, right? So for endothermic reaction, right? So for endothermic reaction, right? For endothermic reaction, your delta H, your delta S, right? Your delta S of your system will be greater than 0, right? So for exothermic reaction, right, the delta S of the surrounding, right, so the surrounding will be greater than 0. And then you have to look at the other term, right, to determine whether it's spontaneous or not, right? So you want compare the magnitude of these two, right? So if they're both positive, right, like the case in A, it's definitely gonna be spontaneous, right? So but if one of them is negative, you have to compare them like you have in B and C. So chapter 20.2 is pretty short, right? So for the homework, we have 2 problems, right? Calculating the delta S of the system and the surrounding, and also determine whether the reaction is spontaneous or not, right? Based on the calculation, based on the sign of the delta S universe. Right, so I'll see you guys in the next lecture.